Hey everyone, welcome to this explainer. Today, we are going to completely demystify the invisible force of electricity. I mean, we use it every single day, we rely on it completely, and yet, it kind of remains this magical, unseen phenomenon. So our goal today is to ground these abstract concepts in the everyday objects you use all the time and reveal the incredible hidden journey that's happening right inside your walls and devices.
So let's just dive right in with a pretty massive question. How does the exact same invisible energy power a simple glowing flashlight, a blistering hot toaster, and a futuristic high-speed levitating train? Honestly, it seems like they should require completely different types of magic, right? But as you'll see, it all comes down to the exact same fundamental rules of physics, just harnessed in totally different ways.
Here is our agenda for the day. We'll be mapping out the invisible journey of an electrical charge by looking at the anatomy of an electric circuit, circuit components and symbols, the heating effect, the magnetic effect, and finally, conductors versus insulators.
Okay, let's start with Section 1, Anatomy of an Electric Circuit.
Before anything exciting can actually happen, we have to define what electric current is. You can think of it a lot like water flowing through a pipe. In physics, current, which we measure in amperes, is literally just the total electric charge flowing through a conductor over a specific period of time. It's basically a constant flowing river of invisible energy. But here's the catch. This journey absolutely requires a closed, continuous path. For our river of charge to actually light up a bulb, the track has to be unbroken. If a switch is flipped off or a wire gets disconnected, well, the track is broken. That creates an open circuit, and the current instantly stops dead in its tracks. With electricity, it is very much all or nothing.
Moving right along to Section 2, Circuit Components and Symbols.
So, when scientists and engineers map out these circuits, they don't sit there and draw highly realistic pictures. I mean, that would take forever, right? Instead, they distill all those complex physical pieces into simple, universal symbols. A wire is just a straight line. A cell has a long positive line and a short negative one. A battery is just multiple cells linked together, and a switch, that's simply two dots that either connect or break the path. Now, technology has vastly evolved how we actually use these components. Take the classic incandescent lamp. It uses a super thin tungsten filament that gets so incredibly hot, it glows. But it wastes a ton of energy as heat. Compare that to the modern LED, which uses a semiconductor. It runs cool, and it's remarkably efficient. The only catch is that LEDs are directional, meaning the positive and negative terminals have to be connected perfectly for them to work.
Let's look at how all these components unite in the real world inside a basic torchlight. You've got cells stacked to form a battery, which pushes current through that metal spring at the back, up through the slide switch, and right into the bulb. The metal casing and the internal wiring form that essential closed loop we need to make it shine.
All right, Section 3, the heating effect. So what happens when the path gets a little difficult for our electrons? If we force a massive amount of current through a very thin or highly resistant wire, what's the immediate physical consequence? Well, the electrons don't just stop. They push through, but definitely at a cost. And that cost is heat. According to Joule's law of heating, the electrical work done to overcome that resistance is transformed directly into thermal energy. And you know what? This isn't a glitch. It's actually a feature. Everyday appliances like your toaster, your iron, or a space heater use coils of highly resistant wire to intentionally turn that electrical struggle into intense, useful heat. But we also use this exact same intense heat to create an absolutely critical safety device, the electric fuse. Inside a fuse is a thin wire designed with a very specific low melting point. If there's a dangerous power surge, the wire instantly heats up and melts. It literally destroys itself to break the circuit. It's sacrificing itself to save your expensive appliances and potentially your home from catching fire.
Next up, Section 4, the magnetic effect.
So back in 1820, a scientist named Hans Christian Ørsted made a world-changing accidental discovery. He noticed that when electric current passes through a standard wire, it forcefully deflects a nearby magnetic compass needle. You turn the switch off, it points north. You turn it on, and it snaps sideways. Ørsted basically proved that an invisible magnetic field is generated simply by electricity flowing through a wire. And this brilliant discovery creates an incredible mechanical loop inside an everyday electric bell. You press the switch, current runs through a wire coil, creating an electromagnet that forcefully pulls an iron bar. Ding! The hammer strikes the gong. But here is the genius part.
That very movement physically breaks the circuit. The magnetism vanishes, a spring pulls the hammer back, the circuit reconnects, and the loop fires again. That rapid-fire switching is exactly what creates a continuous ring. Now, if you scale that exact principle up to a massive industrial level, you get maglev, or magnetic levitation trains. These absolute marvels of engineering eliminate track friction entirely. By using the principles of magnetic attraction and repulsion, electromagnets embedded in both the train and the track literally lift the train upward, while alternating magnetic fields pull and push it forward. It's literally Ørsted's compass experiment and the electric bell concept, amplified to propel thousands of tons of metal at breathtaking speeds.
Finally, Section 5, Conductors versus Insulators.
To actually control all this incredible power, we have to use the right materials. To keep electricity moving smoothly, we use conductors. These are metals like copper and gold that offer very low resistance. But, as we know, electricity is dangerous. So, to keep that flow safely contained, we rely on insulators like plastic, rubber, and ceramics. They completely block the flow, preventing the electricity from escaping and causing disastrous shocks. And here's a quick fun fact for you. Even though we almost exclusively use copper wire because it's pretty inexpensive, silver actually allows electric current to flow more freely than any other metal on Earth. It is the absolute best conductor out there. We just don't wire our houses with it because, well, it would cost an absolute fortune. These materials work side by side every day to keep us safe. Think about a pair of electrician's pliers. The jaws are solid metal, obviously, to cut and grip live wires, but the handles are covered in thick rubber. Why? Because the human body is actually a fantastic conductor of electricity. Without that rubber insulating shield, the electricity would use the electrician's body as the absolute fastest path to the ground. And that really brings our entire journey full circle. From a humble, continuous loop of cells, wires, and switches, this invisible charge branches out to fundamentally shape our world. On one hand, it gives us the heating effect, powering our irons and saving us with fuses. On the other, it gives us the magnetic effect, enabling electromagnets, bells, and towering industrial transportation. As we wrap up our explainer today, I want to leave you with this final thought. We've seen how humanity learned to harness a totally invisible force, transforming it to light up our darkness, cook our food, and propel us forward without any friction. Knowing these foundational rules of physics and seeing how they apply to both a tiny flashlight and a massive train, what will you invent with electricity next? Keep wondering, keep learning, and I'll catch you on the next one.